Hi boys and girls, welcome to a new IB Physics video. In this video, I will include for chapter 3.1 on page 125, all the questions walked through. Basically, you see all the questions are very similar to the IGCSE level. As usual, we will go through the study guide from IBO on this chapter. For understanding, you should know molecular theory, and also you should know the temperature and absolute temperature, which for temperature would be in degrees Celsius. For Fahrenheit, you don't actually need to know that. And for absolute temperature, it should be in Kelvin unit. For internal energy, you should know that it includes for kinetic energy and also for potential energy in terms of the microscopic view. I'm pretty sure you know the rest of the other three. And let's move on to application. Describe a temperature change in terms of internal energy. So basically, you refer to the kinetic energy. Second one is what I mentioned for that two temperature. For the third one, calorimetric techniques is something that you will see in the questions. Not really something that so special. You will see later on in the question. And phase change in terms of molecular behavior is considering the potential energy. And for sketching and interpreting the phase change graphs, I think you will see more on the cognitive question. And the last one is calculating energy change involving specific heat capacity and specific latent heat. We will be mainly doing in this chapter. Yeah, I think one more thing that I want you to pay attention to is this one. The graphs for phase change, which may have axis of temperature versus time, which is very usual, like temperature over time. So it will be something like this maybe, which is very common in IGCSE. But the last one, temperature versus energy, is probably something new for you, and I will show you at the last of this video. And as usual for the equation, nothing new to you, and you'll be only using these two throughout this exercise. For the first question is extremely easy. So it said in general for a hot body brought with a colder body, and of course they, as our experience, we know that their temperature at last will be the same. And now we assume there's no other bodies are nearby. And now it asks you to discuss whether the energy loss is the same as the energy gain by the other one. And the answer is yes, of course. And remember to mention about the reason that there are no other bodies are nearby. That means there are no surrounding air, and therefore there will not be any energy transferred to the air. And due to the conservation of energy, and of course the energy gain equal to the energy lost. For the second question, it asks whether or not the temperature drop is the same as the temperature rise of the other one. And the answer is no, because you can look at this equation. First of all, we know that the energy loss and gain, just like what we mentioned, is the same for different bodies in contact. And you can further deduce this equation in the second part here, and you can see that this temperature change and this temperature change will only be the same when the MC and the other MC are the same. So if this one and this one are not the same, then of course the change of temperature would not be the same. So my answer would be no, except when the two bodies has the same heat capacity. Remember, heat capacity means the mass times specific heat capacity. In general, I'm sure you remember that from IGCSE. For the next question is again very simple. For part 1, you only need to write the formula again, and you substitute all the things you know, you find the answer. Pay attention to the unit, remember to put it on, and also for this one, if you want, you can change it to K -1 if you want, because you know they are the same. For B, I would rather say it's a very redundant question because they didn't change anything except the unit of the delta T temperature change. So so here's my answer here. You can have a look. For the next question is what you're gonna do is again you write temperature gain or supply equal to the energy absorbed by the objects, and therefore supply by, since it's set by the electric heater, so it would be power times time, and the other part will be MC delta T. And therefore you substitute all the things you know, and pay attention that this part is corresponding to the specific heat of that mass for the, well, whatever mass it is. For the other part, that will be the liquid. And since they must have the same temperature change as they were, in contact before the so-called experiment starts, and therefore at the beginning they should both have 15.0 degrees Celsius, and at last they should both have 19.0 degrees Celsius. And that's why you can formulate this equation, and at last you find the answers easily. For the next one is again very similar, and I think I don't need to explain anything. And the assumption for this is again no energy is lost to surrounding. That means mainly the air. Next question is really interesting. So first of all, from the question, after you read it, you should know that for this one, 16 kJ and 1 K would means that for the heat capacity for the tie, well, not the tie, the brake drums will be 16 times 10 to the power 3 joule per Kelvin. That's something that you need to find out in the question, and after that you can proceed on the normal calculation, which start from energy gain equal to energy loss, and you substitute everything inside, and you will find the temperature change, which will be 72 degrees Celsius. Or if you take the G as 10, then you will find the answer as 73.1 degrees Celsius. I guess that's how the textbook answer worked out at last. Next question is again extremely typical for part A. You apply the equation, substitute, you find the answer. For part B, you again energy supply equal to energy absorbed by the object, and at last you find the answer. For the next question, I don't think it's very well designed by the textbook, and they assumed you will go back to a few page previous and look for the specific latent heat of fusion and also heat capacity for aluminum and water, which I have stated here, which you can take reference to. You may want to take the other one. I think for fusion that I take 333.55 kJ per kg here. I took it from the internet, so I think the textbook is having another one, but it doesn't matter. I think the way that you should do is the same. So your answer may change a little bit, and it doesn't really matter. So what you're going to do is again energy loss equal to energy gain, and this is for the ice to melt, and this is for the ice water, well, the water melted from the ice to gain the energy, and the other part is for the water and aluminum, as you can see from the underscript here. Basically you just substitute chunk of figures inside, and you'll find the answer as long as you do it carefully. For the next question, you need the equation of density, which is rho equal to m over v, and you will find the mass of the ice is 1080 kg, and therefore you can happily substitute the number and you'll find the answer very simply. For the next one, again you need to use the density equation here, and For me, I would assume, well, I'll let the unknown AIs for the area of the eyes, and I can proceed on doing the work, and I can use these to represent the mass of eyes, since we don't actually know the volume of the eyes. And after that, don't worry about that. After that, in the next part, you will see that for the eyes area, they will cancel each other, and therefore you can proceed on calculating the time, which is 5 times 10 to the power 4 seconds. I think it will be a better practice to do this instead of I think some of you may try to say or assume area of eye is 1 meter square, or actually you can still find out the exact same answer as this one, but if you want to show a better presentation or you want to show the beauty of physics, I think it's the best to do it in this way. For part B, it asks you why the actual mass of ice melt is less than your answer. In fact, I will actually think the ice melted probably in reality would be more, because I believe the air above the ice should usually absorb, well, not really absorb, but giving out some energy, transferring energy to the eyes instead, not just relying on the radiation from the sun. But anyway, since it asks you to suggest, right, it doesn't matter what kind of reality it should be. Instead, you try to give any possible reason. So the logical thinking is, since the mass of the ice melted is less, and therefore that means the energy absorbed by the ice is less. So probably I think one of the possible reasons could be due to the reflection. So the radiation from the sun, which means of course sunlight, could also be reflected by the ice. So probably what they receive is not 600 watts per meter square. It will be less probably. Or if, well, but I don't think that is that usual, that the air is below 0 degrees, so that energy is also transferred to the air. Energy, well, from the ice is also transferred to the air. But I'm not sure, but I think that's the possible reason. For the next question is the question I like the least in this exercise, because it's too simple and general that they just give you a fixed mass and ask you to calculate all the situation. So I think the most meaningful part is part D. It asks you to compare which state would require the most energy, and I just put a sequence here, which is melting the ice require most energy, followed by warming the water and warming the ice. Actually, you don't even need to calculate, in my opinion. That you can just simply look at the factor here, then you should be able to understand and compare easily. And again, for the specific heat capacity of ice, you need to look from the list on your textbook. Next question, again very typical. That's my answer. You may find a slightly different one if you use another figure for latent heat. Okay, for the next question is not the question that you are expecting to be next. It's a question from Cognitive. Pause the video here and try to do it now, and I'll show you the answers after that. Okay, so here is the answer, and very typical one, like what we try in the lesson. And you can see that what you're gonna do especially is setting up the final temperature TF here, and after that you should be able to find the final temperature as 98 degrees Celsius, and therefore the water would not be boiled in that case. If you somehow calculated, well, if you change the answer, change the question, which may be saying having higher temperature of oil, or maybe more mass for the oil, than the water, then maybe the answer that you calculated would be like, say, 100 and something more degrees Celsius. Then in that case, that would mean the water will be boiled, because of course the water would not be, well, normally in normal pressure would not be higher than 100 degrees Celsius. So the extra energy that you have after 100 degrees Celsius would be used for boiling in that case. But it's a good practice here. If you are happy with the previous question, we can move on to this one, because this one is like a more advanced version of the previous one. So basically the problem is having the ice and the steam and also the water mixed together, all together in one container. So you need to find the final temperature, which is very exciting for me. So for the first part, primarily you want to calculate the energy it requires to melt the ice, and also the energy it requires to condense the steam, and you can see it here. And you will see in the next slide how we can proceed on. So here is from the previous slide, and now we are starting to do the equation again from energy gain equal to energy lost. So the second step is probably the hardest one, because it needs your instinct on whether or not the final temperature will be lying between, of course, for the ice, 0 degrees Celsius, 30 degrees Celsius for water, and lastly for the steam, it will be 100 degrees Celsius. Whether or not the final temperature will lie between here or lie between here. My instinct tells me that it should probably lie in between 30 to 100 degrees Celsius, according to the question. So that's why I would say the energy, well, for the energy gain, that one, it will be used for melting the ice, increasing the temperature for the water from the ice, and also the 30 degrees Celsius water at the beginning. And also for the energy loss will be the energy you somehow you got from the condensing the steam, and also after that you lower down the temperature for the 100 degree Celsius of water after the steam condense. And after that you can do it one by one. For melting the ice, it will be this one. For degrees Celsius one, it will be this one. For 30 degrees Celsius one, will be this one. And for condensing, will be this one, which is what we're calculating the previous slide. And lastly, for 100 degree, that one will be this one. So pay attention that you should put the final temperature correctly. This one is final minus the 0, finals minus the 30, and the last one on the other side will be 100 minus the final. And therefore, after these long chains of numbers, you should be able to find this step. After you put them in correct order, and you will find the final temperature to be 95 degrees Celsius. If you expect the video end here, you are wrong, because you forget I mentioned I will show you a question on temperature against energy for the graph. Here is a MC question from the past paper. Pause the video now and try to figure out which one is the answer. It's a very simple question actually. For this, of course, you need to write the equation energy equal mc delta T, and there are two ways to do it. The first one is, of course, it asks you the gradient of the line. So what you're gonna do is, gradient here means the change of y and change of x. So for this one, it will be delta T. This one will be delta Q. So you can rearrange the equation into delta T over Q, and therefore you can put MC on the other side, so 1 over MC, and therefore the answer will be D. Or another way, you can if you more like the maths way, then you may want to put the delta T here, and you put 1 over mc on the other side together with the Q, and therefore you can compare this with the normal straight line, which is y equal mx plus c. So here Q will be the x and y will be the delta T, and therefore this one will be the gradient m. And for plus c is basically because of the delta T issue, that that means which temperature you start with. Okay, so here finally is the real end of this video. Thanks for watching, and I'll see you next time.